Hi everyone, let's go through this 2012 November A-level paper on paper 3 question 5. Right, this can be found in the notes. Okay, let's run through. Okay, they say malic acid can be, this is a malic acid, has this structure. It can be dehydrated to give a mixture of two isomeric alkene dioic acids, right, with this molecular formula. Okay, so if it's going to be dehydrated means you're going to take away water. I'll take away water from here, the OH from here, and the H from here. So I guess this is where they'll form the double bond. Okay, this is where they'll form the double bond, right? So you should be able to draw these two structures, right? One is cis and one is trans, right? So this is the type of isomerism that exists between these isomers, right? Okay, let's look at the next question, right? So I guess you can do it. Suggest reagents and conditions for dehydration. Usually we just use excess concentrated H2SO4 and heat. Okay, but here I put 170, but heat is actually totally fine, right? Heat is actually totally fine. Okay, let's move on. All right. Okay, then the next question, the pK values of these two acidic groups in one isomer J are 3 and 4.4, whereas the other one is 1.9 and 6.2. They say using the pK values, use the pK values to suggest which isomer produces the more stable anion. So the one that produces the more stable anion, which means imply it is a stronger acid, right? So stronger acid means it must have a higher Ka or lower pKa, right? Higher Ka or pKa. So I'm only going to look at the Ka1, right? I'm going to look at Ka1 for J and for K. So stronger acid also imply it must have a lower pKa. Okay, but in this case, I'm looking only at the first dissociation, right? So lower pKa1, which is actually 1.9 compared to 3 over here. So which means K would be the stronger acid, right? K would actually be the stronger acid, yeah? Okay, and they say explain your answer. So in order to explain which is the stronger acid, right? Which is the strong acid and is the one that forms the more stable anion. So if you could see it, you will realize that actually this is supposed to be K and this would be J. All right, so I'm just going to draw very quickly why K will form a more stable anion. So if you try to draw it nicely, it should look something like this. All right, so when it loses the H plus, right, when it loses the H plus, it becomes O minus, right? So over here, you notice it will form what I call, you can call it hydrogen bond, but you also can call it ion dipole, okay? Ion dipole interaction, or you can call it intramolecular H bond. It's okay, right? So if it forms intramolecular H bond, or you call it ion dipole, this molecule or this ion becomes more stable, right? It becomes more stable, so it can be formed more easily, and it probably give out more H plus. Right, so it's going to be a stronger acid. So essentially, you should be able to tell me K has a smaller pKa value, hence K is the stronger acid. Yeah, so I think I've already answered the next part. Okay, I've answered the next part actually. They say draw the displayed formula of the mono anion produced and explain why it is more stable. So it was exactly what I mentioned. So hopefully you managed to draw this, right? Draw this ion. So you can call it intramolecular hydrogen bond. You can also call it ion dipole. Okay, why can you call it ion dipole? Because after all, this is an ion, and OH here is a dipole, delta plus and a delta minus. Can so we can call it ion dipole. So the H plus is lost readily as the COOH stabilizes the CO minus anion, right? Okay, so where's the COH? I'm just gonna highlight the COH over here stabilizes the CO minus, right? Through the formation of intramolecular hydrogen bond. So this anion should be quite stable. So that makes K a stronger acid. Okay, so let's look at the next part. Explain why pK1 is smaller than pK1 of K. So it's exactly the same answer over here, right? This actually is the same answer here. So it loses, so they're trying to say is K is a stronger acid than J. So it's exactly the same answer, all right? Because it forms intramolecular hydrogen bond, more stable anion, K will be the stronger acid. Yeah. Okay, let's look at the next one. This is the one I'm looking at. This is a bit more tricky. why the pKa2 of K is larger than the pKa2 of J. All right. So what's the pKa2 of K is 6.2. The pKa2 for J is 4.4. So what it really means is this. Okay, let's see what it really means. So I'm just going to draw it out for you very quickly. All right. So I'm going to look at only these two. Right, I'm going to just draw. So I've drawn the Ka1 and K2. Okay, I've drawn the K1 and K2 for isomer K and isomer J. Alright, so this K loses 1 H plus. Alright, loses 1 H plus. And then this one copy down. It loses another H plus. This is your Ka2. Alright, over here, same thing. This is for J. Alright, J loses 1 H plus. This is Ka1. Copy down here. So it loses another H plus. So it loses another H plus from here. So this is loses H plus from here. And then this is K2. So essentially what they're trying to say is this, okay? This is a larger value than this. Okay, larger pKa means smaller Ka. So they're trying to say, maybe I call this K2, I call this K2 and call it J2, all right? So basically they're trying to say why, the question is this, why is K2 a weaker acid? Okay, because it has a larger K2 means it's a weaker acid than J2. Okay, so why is K2, why is this a weaker acid than this? Because it has a larger pK value. So it's exactly the same concept. So if K2 is a weaker acid, means it's more difficult to lose this H plus. Alright, it's more difficult to lose this H plus. And I guess you can tell why is it more difficult to lose the H plus, because there's already intramolecular hydrogen bond. So there's a strong attraction of this H to the O minus, so it's more difficult to lose the H plus, right? So in fact, the answer is still roughly the same. The second H plus, right? This is the, we're talking about, this is the second H plus, the second H plus that we are going to lose, all right? The second H plus is more tightly, is held more tightly by the anion, by ion dipole interaction, or we can call it intramolecular hydrogen bond. Hence, it's more difficult for K to lose its second H plus. So it's definitely more difficult to lose the second H plus, which makes K2 a weaker acid than J2. That's why the Ka2 is larger than, of K is actually larger than the Ka2 of J. Right? So this is actually the answer for the two parts are still about the hydrogen bond. A still is about the hydrogen bond. Alright, okay, let's move on to the next question. Okay, so over here, if you look at this next question here, they say gently heating anhydrous crystal of one of the isomers. So I drew out for you K and J again, and they say it produces, when you heat it, it produces a neutral compound L, which does not react with sodium metal, or give a precipitate with 2,4-DN-pH. So it says something about L. L is not carbonyl. Okay, firstly, it's not carbonyl. Right, doesn't give a PPT with, so it's not carbonyl. Doesn't react with sodium metal, so absence of OH. So you must take away OH, right? There's no OH at all. So if you look at the molecular formula of K or J, the molecular formula, you know, is actually C4H4O4. So when it became L, okay, when it became L, you realize when it was heating, it became L. So L is C4H2O3. So if you look at the molecular formula, you will realize that they took away water. Alright, they took away water. So the way we can take away water from either K or L, I guess the best way to do it is this one here. You take away the OH from here and the H from here. Can you see that? So you take away water, take away OH from the acid and the H from the other acid. So the mechanism could actually work like this, okay? The mechanism could actually work like this, right? So this O is delta minus, C is delta, this, wrong, C. O is delta minus, so this is delta minus and C is delta plus. And the lone pair of O here could actually function a bit like a nucleophile, and it could actually attack this carbon, okay? And what happens, you will take away the H from here and the OH from here. Can you see that? So it could happen in that manner. Right? So K is probably the one that forms L. Alright, so I'm going to draw compound L now. Alright, so this is my compound L. Can you see that? This is my compound L. Alright, okay, let me take away this first. Actually, I should take away this. Okay, let's see how you form M. They say compound L reacts with ammonia to give M. Alright, to give M. So I'm going to react with ammonia. I'm going to react with ammonia. So it says, what did they say about this L, right? So you got L already. So it gives a compound M, all right, reacts with ammonia to give a compound M, which gives a salt on reaction with sodium hydroxide. So what does it say about M? M can give a salt with sodium hydroxide, means M should still be a carboxylic acid, right? M should still be a carboxylic acid. And M decolorizes aqueous bromine, which says something about M. M is alkene. Okay, M is alkene. So M is still a carboxylic acid and it's still an alkene. Alright, so let's see how it works. Okay, roughly you can roughly tell how the mechanism works. So I'm just going to draw this out. So N, so imagine this ammonia, right? Ammonia could function as a nucleophile again. So there's a lone pair in this N. I can just put a delta minus. Okay, I'll just keep it very simple. I'm just not going to go in detail. So the carbon here is delta plus, and the lone pair N can actually attack this carbon. Okay, this bond here will break. Okay, I can see that this bond here could actually break, and one of the bond here could actually break. Okay, so it's like a bit like hydrolysis of the ester, right? Like it seems like it. Okay, so let's draw the structure then. So you will end up getting OC. Just draw nicely. CH double bond CH. So this carbon becomes CO. CO. Okay, because you can see that this NH2 here will join to this carbon, so become NH2, right? And if this H will go to this O here, can you see that? So become COOH. So it fits into the formula because you still have a carboxylic acid. So really you still have a carboxylic acid and you still have an alkene. So this is the structure of M. Alright, so that's why you could get this as being M. Alright, are you me? Alright. Okay, the next part. So actually, yes, okay, so yeah. So write equations for all reactions, explain the observation. So this M. So I'm going to write the equation for the next two. So I will draw M nicely. Alright. So M will react with sodium hydroxide. So I guess this is sodium hydroxide. Okay, so this is acid-base reaction. Acid-base reaction. You can probably complete it yourself even. Okay, because it asked me to write the equation, right? So I have to write the equation. So this becomes COO minus Na plus, right? So this is the salt. Okay, this is salt. So acid plus base give you salt. Okay, how about the second one? The compound M decolorizes bromine. So the decolorizes bromine, I'm just going to write this equation plus Br, okay, plus water. Okay, it's just Br2, sorry, plus water. So I'm going to put Br and an OH, right? Br and an OH. Okay, NH2, all right. So this is a H first. Okay, so I'm going to add Br and an OH. So I guess I think this type of question you probably can use either or, right? They won't penalize you. So I put Br here and an OH here. Okay, and probably because it's a balanced equation, the side product here is HBr. Okay, so they say write equation. So this is how I'll write it. Okay, and it's already balanced. Okay, let's look at the next part. Okay, let's look at the next part. When malic acid is heated with acidified dichromate, compound N is formed. All right, so let's look at it. So this malic acid, okay, when it's heated with acidite dichromate. So dichromate is an oxidizing agent. It'll probably oxidize malic acid. So I'm going to just draw what I think it should be. All right, so if it's going to be oxidized, I guess I can see that this part is a secondary alcohol and the rest are carboxylic acid. So I'll probably draw the secondary alcohol being oxidized to a ketone. Okay, being oxidized to a ketone. So this is what it should look like. So it becomes a ketone. All right, and the rest will still stays the same. So this is my structure of N. So let's see whether it makes sense. Heating N in an inert solvent for several hours produces P and a gas Q. Both N and P react with 2,4-DN which means N and P both are carbonyl. N and P are both carbonyl. Right, so which is correct because N has a carbonyl group here. This is a ketone. Okay, so P also gives a yellow PPT with aqueous alkaline iodine. Alright, so let me try to draw P. So it's a ketone, it's a carbonyl, and it gives a yellow PPT with aqueous alkaline iodine. I'm trying to draw P now. So I'm just thinking that P should look something like this. Since it's a carbonyl and it can give you a positive iodoform, it should look something like this. If you look at the molecular formula of P is a molecular formula C3H4O3, right? So I have drawn 2 carbon already. So I've drawn 2 carbon, yeah? So I need to have 1 more carbon. And you notice I have to draw 2 more oxygen. I have 1 oxygen here, but I have to draw 3. So I've drawn 2 more oxygen and 1 more H. So 2 more oxygen and 1 more H is probably looking something like this, right? So carboxylic acid. So this is definitely my P. Okay, so it's a ketone, right? It's a methyl ketone, right? It can undergo positive iodoform. All right, and they ask me what happens to the other product. So they say heating for several hours, right? Heating this for several hours, you get P and Q. Okay, and this is a gas Q. Okay, so if you look at it carefully, all right, you probably can guess what is Q already. So P actually, it looks over here, looks pretty much the same. Can you see P? This is CH3, right? So I'm going to take away the H from here. Can you see? So you get CH3. Okay, maybe it's not very clear, but I mean this H and this H and this CH3, this H2 combined to give you CH3. So whatever is left is actually this part here. All right, so I'm making an intelligent guess that gas Q should be carbon dioxide. Right? So that's how we do this question.